Welcome back to Deeper into Mathematics. And today we'll be discussing a new topic, that is functions. And functions is correlated with the concept of set and relation, which you need to be thorough with in order to understand what an actual function's working is and to understand in depth about the working of the functions. So, let us get started. So, what is a function basically? So, function is to show in terms of set by set theory. I'll write it in yellow so that concepts are in yellow. By set theory. If we see, the functions indicate that A is related, set A is related to set B in some way by a function. And function is a type of relation. For example, let us discuss as if this is set A having, I'll write the name outside. This is set A having elements 1, 2, 3, 4. And this is set B having elements A, B, I'll write them small as A, B, C, D, E. So there is a certain relation like this which we can see. And now we have learnt about one-to-one functions, many-to-one functions, and all the theory of bijective, surjective, and injective functions, which will injective relations. Sorry, so that will all come into play in functions, but it would be in handy and not that much application based. So we can see like this over here. This is what a function means by set theory. And if we see it in an equational form, then a function can be well represented by y equal to f of x. So this is how a function is written in general form, y equal to f of x. And now let us discuss one-to-one, many-to-one functions. So before going into one-to-one functions, let us quickly revise the set theory, what all these things are, these things, and how, what are they called as, and then we'll move further with the actual types of functions that exist. So, quick revision from sets. So, let us get started. First of all, let me again draw two sets. This is set A and this is set B, and set A has elements 1, 2, 3, 4, and B has elements small a, small b, small c, and small d. And now there is a relation between these both like this. This is denoted by A is related to B. We don't write the R. It is self-understood that there's a relation now. And now, what is set A? If we see in the theory of functions, then set A can also be called, just a minute, set A can also be called as the domain of the function. And this is the output. I'll write this one as input and this one as the range. of function. This is the output that we get. So, how will we explain this? So, let us understand this in terms of a small thought experiment. So, there is this simple machine. I am representing it by a box and I'm writing on it machine. And this machine is doing a specific work of increasing the size of a particular object. So case one is I put a small object and I set a limit of increasing by 2 times. So the object comes out of this machine this much big. This is the first thing. And then if I put an object this big, then this much big object becomes twice, we can say. And the, if I put a bigger object, let us assume it is to be infinity, then I would get a much bigger object that is also infinity. So this is what we can understand from here. I'll draw it like this. So this machine is nothing else but it is the function, and over here this items that we are putting, which we can say as the ingredients, or we can say the raw materials, they are our input, that is our domain, and the finished products that we are getting, these are nothing but our output, which can be called as the range. So on giving a small input, will get a comparatively small output. On giving a big input, we can get a comparatively big output. And now to see an mathematical example, we can take the example of y equals to x square, just as an example. If we put the value of x as 1, y is 1, x as 2, y is 4, x as 3, y is 9, and x as 4, y is 16, x as 5, y is 25. And so we can relate this machine to this machine. They work the same way. But this one, the above one, is mechanical, and this one is mathematical. So this is just an example to understand how we can do. So now that we have understood what a domain codomain range is, let us understand another term, that is codomain. What is the codomain? So now the example I took over here was the one where the range and the codomain matched. But if we see sometimes, this is set A that has elements A, B, C and D. This is B which has elements small a, B, C, D, E. And if I map them like this, A, B, C. So this E has no input, but still it exists in set A. So now I can say B, that is A, B, C, D, E. This is the codomain. And if we write the set of A, B, C, D, this is our range. So now here comes the definition of range. How we can define the range? The element in the codomain that is related to another element in the domain, such elements altogether are called range collectively. And what is a domain? It is the input that we provide to the function. And what is codomain? It we can say that the codomain is B. In this case, the codomain is B. Example. So now we can derive from the set theory a small equation that f of A is a subset of B. That means f of A is the range. I'll write it in another color. This is our range is a subset of our codomain. So now a common misconception that students have is that range and codomain are same. So I'm writing it in bold in large letters. Range is not always equal to codomain. Over here I could have taken B as set of all real numbers and A could be the set of all real numbers, and I could have written an equation y equals to 1 by x. So now over here we would have excluded 0 from our range. So this equation could be a prime example to understand this. Let us move further onto the types of functions. This is an important part from which most of the questions are asked. Types of functions. So the first type of function is one-one function, that is also called as one-to-one function. And one-to-one function, it has, like, let us take an example to understand this once again. This is B and here we have 1 2 3 4 5, and again we have, let's not take 5, that's too much, and A B C and D, and I relate them in such a way that every element in codomain, I am writing this and this is to be learned by heart. Every element in codomain has its image in the domain. Such a function is one-one function. So over here we can see that the letter A is connected to 1, B is connected to 2, C is connected to 3 and D is connected to 4. So now if I introduce E. Right now I'm erasing E, and I can write E to be E to be is 1 1 function. And now if I add an E over here, and it is not connected to any element, an image, it doesn't have an image in its domain. We can state it mathematically like this: it does not have an image in the domain, then sorry, it does not have a pre-image. Every image must have a pre-image. Image is over here and the pre-image is over here. So I should add pre-image in the domain. Such a function is 1 1 function. So now is 1 1, but as E, the image does not have any its pre-image, then it would not be 1 1. So now I'm removing this. Okay, this is understood. And now let's move further. The second type of function is many to one function, and now let us understand this. The word many to one. Now here it was 1 1. So now let us assign one for A and one for B. Many for A and many for B. And you will understand why I'm doing this, so that it becomes easy for you to learn it. So A again has 1 2 3 and 4. B has A, B, C and D. And now I relate them in this way. And yes, let's not take D. This 4 is related to B. So now one into one function can be said to be a function where many elements of A, let me change the color, many elements in the domain, that is the pre-image, one image has many pre-images. Such a function is called as a many to one function. One image has many pre-images. So now this is what we can take as an example. The easiest example is y is x square. So if I take y as 4, then x can be plus 2 or x can be minus 2. So this is a many to one function. I'll write it over here. And let us now discuss something which is very much important, that how to identify it is a function or not. Anything is a function or not. What is a function? So what is not a function we shall decide, because everything rest other things are a function. So let me take set A again, 1 2 3 and 4. Then set B of A, B, C, D. And if I start to connect them like this, watch carefully how I'm connecting them. And this is over here and 4 to D. And we have kept the 3 vacant, let it be. It does not come in handy. But now the thing to notice is that one pre-image has two images. So now let us come to this example that we understood what a function is. We put an object of, let's say, this much size, and it gave us two objects that are of this much size and that is of the same size. So we won't say it is multiplying by 2. So the machine is not working properly, we would say. And in mathematical terms, this is not a function. So the not is important over here. Such pre-images having more than one images, such a relation. Now the theory is getting generalized and is being attached to the certain relation is not a function. This is a very big lack of understanding that the students have about what a function is, and I want you to have it crystal clear. That's why I gave you this example and this example, and let us denote it like this, the relation, and this simple machine example. So if you in case ever forget it, then let this examples come to your mind, and then you decide whether the given relation is a function or not. So now let us continue to the third type of function, that is an onto function. Now the onto function, which can also be called as surjections, and the one function is called as injection. It's like injecting and getting an output. That's there, not a lot of things. And the onto function is called as surjection. So the theory for onto function is every element of B, every element of B has at least one pre-image. Then the function is an onto function. So let this be set A, B, C, D, and let this be set B. Now I'm making it big, and let it be 1, 2, 3, 4, 5. And now for it to be a function 1 to 1, onto function, then an element of B, every element of B, this is a critical condition, must have at least one, I'll write it, every image must have at least one pre-image. So it can be 2, it can be 3. We can state it like this. And if B is related to then 2, and I'm just randomly tracing. So now every element of the codomain is related to the domain. We can also write it like this. Of codomain is related to the domain. I'll write an or in between. Both the statements mean the same thing, but it can't be that one pre-image has two images, because it would violate the definition of being a function that we discussed over here. So I'll remove this arrow and I'll quickly draw this up. So now that we have finished three of the functions, let us go into understanding what an into function is. An into function, this simple trick is to know into and onto are each inverse to each other. If a function is not onto function, then it is an into function. But then too we'll discuss how a function cannot be an how a function cannot be an onto function and can be an into function. That's just the same thing. I'll draw A, B, C, D, 1, 2, 3, 4. So now I'm just going to connect those at random. So this was 1, this was 2, this was 3, and D is also connected to 4. D is also connected to 3. So now 4 does not have any pre-image. Thus the function A is related to B in this time is an on into function, and it is like, if a function is, I'll write it, if a function is not onto, then it is into. And now you have got it clear with this. So now let us understand another type of functions, that is fifth type, bijective functions. Bijective function. And a bijective function is a function, the word bi means two. So what are those two conditions? The two conditions are, first one, it should be 1 function, and the second one, it should be on to function. So now what the onto function is, we have discussed it all, and now I'll draw a rough example of what it is. It is just easy. Let here be A, B, C, D, and let our codomain have elements 1, 2, 3, and 4. This is 2. And now I'm going to relate them one by one. So now in this case, A related to B is a bijective function. Yes, this is very important. Mostly in examinations, the terms bijective function, then surjective function, and injective functions is used. So we need to know what an injective, surjective, or bijective function denotes. And we have mentioned it all, so no need to go. Now that we have understood this major type of functions, let us discuss some other type of functions that are also in use but not asked that much. So the fifth one is a constant function, which can be denoted graphically as y equal to phi. So at any value of x, y would be phi, and the line would be parallel to which axis. That is a very important thing to know. So the line y equal to 5 would be parallel to x-axis, and I'm going to, this is the line, this is origin, this is y-axis, sorry, this is origin, this is y-axis, x-axis, and this is the line y is equal to 5. So at any value of x, the function gives same output. Such a function is a constant function. This is an obvious thing, but still I am discussing it. And now what an identity function is. This is something that not most of the people have known about identity function. So identity function is a straight line passing through the origin, which is inclined at an angle 45 degree. So identity function can be a function which is related, A is related to A, and the elements are 1 comma 1 of that relation. Elements are 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4. And these are the elements that we get from the line passing through the origin and inclined at an angle of 45 degree. And I'm going to draw it. Yes, this is that line and I'm going to extend it now. This is line y equal to x, inclined at an angle of 45 degree. So for every value of x, there would be a y which would be same as x, because we have the equation function defined as y equal to x. And this can be, identity function can be seen as an application of identity functions can be discussed in trigonometric identities. So now if I give you that y sine square x equal to 1 minus cos square y, then write the set having elements x comma y, and those elements would be, this is a relation that we are defining, this is a relation, that is an equation, a function we can say now that we are defining, and the elements would be pi comma pi, pi by 2 comma pi by 2, 3 pi by 2, 3 pi by 2. In fact, in basically any real number with the same real number. This is an identity function. So we can say that, I'll write it with this color, any trigonometric identity is an identity function. So now let us discuss some other few types of functions based on the value of function. First, based on the first one is a polynomial function. A polynomial function is defined, you can basically see it as f of x equals to some constant k1 into x to the power n plus k2 plus x to the power n minus 1 plus k3 x to the power, oh, there's no addition in between, it's a multiplication, k3 into x to the power n minus 2 and so on. This is a polynomial function, and it has a degree n, where n is a non-negative integer, n is an integer that is always positive. So this is a polynomial function. Then the second one is a rational function. A rational function is, as we saw, h by k, which can now be written in a functional form as f of x upon g of x. These are two functions having the input x, but their outputs are different and they are being divided. This is the theory where we define, in this case we define that k is non-zero, and now here we define g of x is not equal to 0, and it can, the f of x and g of x are polynomial. So now this is here. So the third type of function is an algebraic function. So algebraic function is a, I can say, binary function that deals with multiplication. Oh, I'll write the symbols. They are important. Easy. Multiplication, division, addition, or subtraction. Y equals to x minus 5 is an algebraic function. Easy. And it does not involve any second degree or third degree. So we can say algebraic functions are linear functions. Linear function. The fourth type is transcendental functions. These are the functions that are not algebraic. So if in a particular question it is mentioned that an above equation is a transcendental function, then it indicates that the above equation is not an algebraic equation, that is not a linear equation. It it can be in the form of exponential functions, B logarithmic, that is a form of exponential, C trigonometric, that is again not a linear function, inverse trigonometric, or even we can see as a polynomial. And we can say algebraic functions are the functions which are of linear. So now if I write a quadratic equation, y is equals to x minus 2 into x plus 3, now this is an algebraic function. But now if I solve it as x square plus 3x minus 2x plus x minus 6 is equal to f of x, now it goes into the polynomial function. So now we can say they are interrelated. This is something to note. I'll write it here. This is an algebraic function and this is a polynomial. Yes. So these are some of the types. So yes, we have completed with the types of functions. And now we'll be seeing some types of functions that are defined, standard types of functions. So till now, if all the theory is clear, then we'll be putting it to application and understanding, and we'll understand each and every type of function along with identifying what its range is, then its range, domain, and also the graph of a particular function. So the first function is the modulus function. You might have heard of the term mod x. That is, if I put mod of minus 5 is 5, mod of 5 is also 5. And now let us see what a modulus function actually is. So modulus function is defined as if it is minus x, it is minus x. If x is less than 0, 0 if x is equal to 0, and plus x if x is greater than 0. Thus, we can say that mod of x is always greater than 0. This is an important property of modulus. And now that you have known modulus function, let us see the graph of mod x. This is the x-axis, this is the y-axis. And now the mod x graph goes something like this. I'll rearrange this line a little bit. It needs to touch the origin. Yes, now it is correct. So this is the origin, and this is where x is greater than 0, and this is where x is less than 0. So even for the negative values of x, the function is positive, and even for positive value of x, the function is positive. And this inclination is 45 degree, and from here it is 45 degree. So this is y equal to mod of x. We have defined this function like this. And another property that is obvious is mod of minus x is equal to mod of x. This is something that we don't need to mention, but still I'm mentioning. Okay, so now let us discuss about the range of the function. So let us first discuss about the domain, because domain is important. It takes all real numbers as an input and gives all real numbers as the output. So this is the domain and the range. Now let us discuss the next function, and that is greatest integer function. So now this function is defined as, like, it is denoted by box of x, and if a number is 1.37529, then x is this, then box of x, that is box of 1.37529, would be the lowest integer that is seen. So it is in this case 1. Box of x in this case is 1. Now let us take x as, this is example 1, this is example 2. So now let us take x as minus 2.1. So now the greatest integer, lowest integer that is less than this is for minus 2.1. Let us see where minus 2.1 comes. This is 0, this is minus 2, and the minus 2.1 goes somewhere over here, and this is minus 3, let us assume. Okay, the things are a bit squashy. So minus 2.1, and this is minus 2. So the lowest integer in this case is minus 3. This is very important. So box of x in this case would be minus 3. So we need to know these things, and we don't have to make mistakes. And the range of x, if x is a real number and n plus 1 are such that they are between like this, then we can say that the box of x is equal to n. This is how we have defined the function greatest integer function. This is my shortcut for writing it. So now let us draw the graph for this function. It is damn easy, and from its looking nature we have derived a name for it. And yes, so now let us draw the graph. So let us start putting values from origin. So 0 to 0.9, the function would be over here touching, and I'll draw a hollow over here at 1, and the function would jump here at 1, and it would continue till 2, and this is 2, then it would jump at 2 and continue till 3, like this nature, and it would go on increasing. And if you see on the negative side, so here the function goes something like this is -1, then it would bounce off over here. These are hollow circles. Let me draw the circle correctly. And now the function jumps back down, and now it is -2. So we can see it is stepwise increasing function. So it is called as a step function, is another name for greatest integer function. So now let us discuss about the domain and the range of this function. The domain and the range. So domain has all the real numbers, and the range, that is the output that comes, is seen on the y-axis. So if we see on the y-axis, we are getting integers, may that be positive, may that be negative. So we write integers. So we are clear with the step function 2. Now let us go to another function that is important, is that is fractional part function. And that is denoted generally by this. And now what is the definition of fractional part of x is that the fractional part of x is x minus greatest integer of x. So now example, let x be equal to 2.1. So box, like, fractional part of x would be 2.1 minus box of 2.1, that is 2.1 minus 2, that is write this in bracket, 0.1. So this is fractional part of x. So the name itself now suggests that it is the fractional part of x, that is part after decimal. Now we have to take care in case of the negative number. Let x be equal to minus 2.1. So now fractional part of x would be, according to our definition, we are going, so let me first highlight this definition because it is important and we would need it much many times, as you realize in questions. So minus of 2.1 minus box of minus of 2.1, and we have seen earlier, oh sorry, minus of 2.1 minus box of minus of 2.1. So we have seen that box of minus of 2.1 is -3, and there's a minus going outside. So now minus 2.1 plus 3, and so now in this case, if we subtract 3 minus 2.1, that is 0.9. So the fractional part of x has changed over here for negative numbers. And now after seeing the graph, you might understand how the graph looks, and you may understand how this is coming. So let us draw the coordinate axes and name them, because the naming is always important. So this is x-axis, this is y-axis. Let me first show the integers 1, 2, 3, 4, -1, -2, -3. Here is our 1. And so now how is fractional part of x? So it goes from 0 till 1, and it doesn't touch 1, because you can't say the fractional part is 1. You can understand it, like, you can't say the decimals to be all 0. So now if I take an integer and I subtract an integer minus its box of x, then it will be 0, but it cannot be 1. So this is the first one. Let it be a bit correct. Okay, something like this. I should have drawn it. So it is this line, and then from 1 to 2 again like this, 2 to 3, and then 3 to 4, then just touches 1. Okay, so now that, and I'll make all this touching as hollow, and I'll show you in a minute why. Yes. So now at integers, if we take x as, oh, let me change color. Let x be equal to 1, then fractional part of x is x minus box of x. So it will be 1 minus box of 1, that is 1 minus 1 is 0. So fractional part of 1 would be 0. So the graph immediately goes down over here at integers. And now let us discuss the domain and range. So the domain is all real numbers, and the range is I'll denote it as 0, then a number is less than 1. So the range is greater than or equal to 0, when the output, I mean the input, is an integer and is just 0.9, as we saw over there in the cases, like 2.9 or minus 2.1, these cases. So now that we have discussed about fractional part of x, let us move further and understand the signum function. This was C, now D. Signum function. And now the signum function is denoted as SGN of x. This is the denotation. So the signum function is defined for a value x as mod of x. Okay, sorry. So signum of x is defined as mod x by x for x not equal to 0, and for x, and if x is equal to 0, then signum of x is x. I mean signum of 0 is 0, and signum of x, it depends what it is. So let us see the signum of x for 3 cases. Mod x by x when x is greater than 0. So I should write over here 1, as mod x would be positive and x would also be positive. 0 if when x is equal to 0, and minus 1 when x is less than 0. That is, mod of x would be positive upon x, that would be negative. Let us take a number minus 2 upon minus 2, that would be 2 upon minus 2, that would be minus 1. So now let us see the graph. This is one of the easiest graph in the whole of the functions except for the modulus. And just a minute, actually. So this is x-axis, this is y-axis, and the graph goes as like this. This over here. Yes, and both of them are hollow because at 0, I'll make it dark, at 0 the function signum of x is 0, and at all the positive values x greater than 0 signum of x is 1, and for x less than 0 signum of x is less than, it is minus 1. So the domain is all real numbers, and the range is, this is how we write in as per the set theory, -1, 0 and 1. These are the three numbers that are only there. So for any real number, with that we have completed some important types of functions, and now let us discuss two more types of functions, and three more types to say, and after that we will complete our chapter. Yes, so let us go. Just a minute. So the first type again, types of functions. So the first type of function is an odd function that can be defined in the equational format as f of minus x equal to minus of f of x for all x belonging to real numbers. Let us define it properly. For all x belonging to the A, that is the domain. So now what this equation means, this is a very important equation that you should not at all forget. This means, let us take an example. Example is pretty clear. Let the function be f of x be sin x. So sin x, if we put let x be equal to minus x, so sine of minus x would be minus of sine of x. So now this proves that minus of f of x equal to f of minus x. F of minus x, and this is f of x. So we can say that sin x is an odd function. And the second type of function, now you might have guessed, would be even function, where f of x equal to f of minus x. And now the immediate example from trigonometry should come to you, and that should strike you, is of cos x. Let us complete the definition of x belonging to domain. So let us take the example of cos of x equal to f of x. Let x be equal to minus x. Therefore, cos of minus x equals to cos x. Therefore, we can say that f of minus x equal to f of x. That can be denoted. I am denoting also. So here I'll write cos x. Why am I writing cosec? Cosine function is an even function. So now if we keep these examples, little examples in our mind, then it would be easy to remember what an even function is and what an odd function is. Now the last type of function that we are going to discuss is an inverse function. And now the first thing is, if x is related to y is can be inversible if there exists a function y. Okay, there exists a function y to the y is related to x such that g of f is equal to ix and f of g is equal to iy. So what this means, g of f means g of f of x is equal to ix, a certain number, and f of g of x is equal to iy, and both are integers or maybe a number, another number. So it says that its inverse exists only if both the numbers exist as g of f of x, and the condition is, and we are denoting that g is inverse of f, and we can write it as g equals to f inverse of x, and this is how we are denoting the things. So if f is invertible, then f must be bijective, so that f, for condition that function f to be invertible, it must be bijective. Bijective means two things, that is onto and one function. It must be a one-to-one function and an onto function. So only then a function exists. If the inverse of a function exists, then it is said to be invertible. And the inverse of a function, if exists, then it is unique. These are some important things. So now let us take a simple example of f of x equal to y equal to x, and similarly f inverse of x then becomes the opposite, that is x equal to y. So now how this thing goes, and another important thing is during inverse, domain becomes the range and range becomes the domain. So I'll make two separate underlines. Domain becomes range and range becomes the domain. So let me define this function as g of x, and now let us draw the graph of these two functions to actually understand what is happening. So this is x-axis, this is y-axis. So now y equal to x, we all know that line, so I'm drawing that line as it is. Yep, I'm extending it. Oh, I'm extending this line backward, and I'm writing y equal to x, and now x equal to y. So now x becomes our y and our y becomes our x. So now I put a value of y and then I get x as an output. So it is the same line, y equal to x equal to y is the same line as y equal to x. And another thing to note is inverse function is mirrored along the line y equal to x. That's why we are seeing the mirror of y equal to x on y equal to x. But now if I would have taken a random function like this, then let this be f of x, then f inverse of x might have looked something as the mirror, and that would go something like this. It is not accurate. F inverse of x. So this was something. Okay, I have assigned f already. So let it be k inverse of x, and I'm changing here f no f kx k inverse of x. This is it. And now we have completed with an important theory of functions. So now let us move to the functional equations. This is very important. So f of x is a function. Now we understood about the function, and k belongs to positive real numbers such that number 1, if f of x plus y is equal to f of x into f of y, then f of x is equal to k to the power x. We have to learn this, how the equations look, because they might come ready handed. If f of x plus y is equal to f of x plus f of y, then simply f of x is k times x. Third thing, f of x into y is equal to f of x plus f of y. We can learn this one as the log one. So in this case, f of x, then f of x is log x to the power k to the base a. I'm erasing this k from here. So the fourth equation, if f of x is polynomial such that f of x plus f of 1 by x is equal to f of x into f of 1 by x, then f of x is equal to 1 plus minus x to the power n. Fifth one, f of x plus y is equal plus, sorry, x plus y plus f of x minus y is equal to 2 times f of x, f of y, then f of x is equal to k to the power of x plus k to the power minus x upon 2, or simply cos of x, because this is the equation of the cosine function, and thus we write it equal to cosine. So now this one is not that much important, not much important, because there are other various types of functions like the sine function where there's a minus in between, so we don't have to look into it. But these four types are very much important. This f to the power, okay, just a minute, I'll make a box, good one. This equation, or let's say this equation, or let's say this equation, or even this one, max to max, if the paper is difficult, then they would ask about this difficult questions. So this theory of functional equations is of less to be of practical orientation and more to be a learnt of, because there is no such trick that we have, and these are ready standard functions which you should know along with the other types of functions that we discussed in today's lecture. And with that, we end with the topic of functions. Thank you.